Hello, friend. My name is Derek Carter, and in this video, I'm continuing talking about the C programming language. We're using Chapter 6 of the Kernighan-Ritchie textbook here. Bring that up. In this case, this video is going to be over kind of Chapter 6 on structures. It's probably be shorter than the previous video. I mostly just wanted to go over like structures, pointers to structures. Maybe touch a little bit on like structures and functions here. Okay, so we're mostly just looking at the basics of structures and the pointers to structures in this video here. But once again, I do recommend the C programming language book. It's easy to get copies of this. There's lots of good stuff in general on data structures and algorithms and other stuff, so you might want to check it out. So let's see here. So a structure is a collection of one or more variables, possibly of different types, grouped together under a single name for convenient processing. So this is really a very generic idea in computer science. So these might be called records, structures, user-defined types. Basically, a row in a database is really a structure. So anytime you're collecting multiple fields, multiple different types of data together into a single item for convenience of processing, you have this concept. And so in the basic ANSI C language, the structure defines a new type. So it is an example of user-defined data type. So once you define a structure, you can declare variables of that type. But the basic operator you can use with the structure is the member operator or the member access operator. Okay, so I'll show an example of this, but basically, we might do a struct like this if we need to have a new data type that holds the XY coordinates for a point for some sort of a graphing application. We might define a structure like this that has two member variables. Both of them are integers, so the types of the members don't have to all be the same type. So array, if you declare an array, all the items in an array are going to be the same type. But for a structure, they can be of different types in here. But this structure that we're showing as an example only has two integers. If you want to declare a variable of that type, we could use a type def, but we can use just the struct and then the name of the struct. So here we would have one variable called pt. We have another variable called max point, and you can actually initialize these if you know what are the member fields. So this would initialize the two integer member fields to be 320 and 200 respectively. When you declare a structure, don't forget the semicolon at the end here. So most code blocks don't have a semicolon, but a structure is different. So when you're defining a structure, you're using the open and closing curly braces as part of the syntax, but then there's a semicolon at the end. So that's a difference between a structure defining a user-defined data type and curly braces around a code block in C here. So I'm not going to really have slides here talking about, you can create an array of structures. So we only show declaring a variable, a single structure here, but I could have an array of structures. You can pass structures into functions and return them as the result from functions. So in a previous video, we showed the fstat function call. So we actually did run across structures. So for example, in our XV6, there's a definition of the stat structure for getting information about files or device files in a file system or directories in a file system. So it's just a collection of the device number, the inode number, the type, number of links, and the size. Typically, when we're using structures in this class, we're not going to pass in. So here, for example, this is how we will normally return back a structure from a function. We'll actually just pass in a reference, right? So here's another example of passing something by reference. The fstat function is expecting a pointer or a reference to a structure. So we first allocate enough memory to hold a structure, but we pass in a reference to that and it fills it in. Right? So that's typically how we're going to be passing around structures to system calls in the XV6 system call API. So you can also declare and use a pointer to a struct just like a pointer to any basic built-in defined data type. But there's a special operator, so you'll see this used a lot in the code in this class here, that will do basically kind of doing two things at once. It's both doing the member access and it's dereferencing at the same time. So if you have a pointer to a structure, you can use this arrow, I usually just call it the arrow, to simultaneously dereference and access a member, okay? So I'm going to spend a little bit of time on this example one because this has some code that's relevant to the assignment that you should be doing for the class this week. So you'll have to do some manipulations like this to understand how things are laid out in memory and to use pointers to access a stream of bytes in different ways, okay? So from our previous video, you should kind of understand what we show here. So we have a structure with a bunch of different member variables. We're using different types this time. So we've got one that's just an address, so a pointer to a character, or possibly a pointer to an array of characters, an integer, a short. So the integer is 4 bytes, short is 2 bytes. So I'll spend some time on this one, but so I just wanted to mention here, so we're showing, say, examples of the member access operator. So we're initializing all of these S structure, but also here's an example of that operator that both dereferences. So since SP is pointing to, it has the address of the structure S, I can ask it to dereference and also access the num1 member inside the structure here simultaneously with one operation. So the result of that should be the integer, the full 4-byte integer num1 gets displayed. Okay, so this is a different example one from the previous video. So just as a reminder, I won't show these steps, but I've already copied this into my user code for the XV6 operating system, and I added the entry to the makefile so that we can build it and run it. So we should have the example one here. Well, I'll go ahead and run it here because it's just outputting a bunch of stuff here. So let's look at it. So first of all, we have the structure that we showed on the slide here. So count up the number of bytes that we have, right? And note, so when we allocate an array like this, all 8 bytes are actually going to be part of the structure here. So this will get allocated as part of the allocation here. So, we could have arbitrarily made that a different number, but an address, a pointer is going to be 8 bytes, integer is 4 bytes, short integers are 2 bytes, characters are 1 byte. So the total is 12, 14, 15, 23 bytes. So we have 23 bytes. Probably should have added that in here. So like we showed on the slide, we just create an instance of our user-defined record or user-defined data type. So S is a structure. Again, remember, don't forget the semicolon here. So these kinds of curly braces around a structure are different than the curly braces around a code block, like our main code block here. Whenever you're doing a structure or a class like this, you have to end them with a semicolon like this. So here we're just initializing all these. So this is a pointer, so we just initialize it to a constant character array. We initialize num1 and 2. So here, it would also be good for this class that you understand and can convert between hexadecimal and decimal and binary. So whenever you have something that's 4 bytes, if you represent it as hexadecimal, each character in a hexadecimal is actually going to represent 4 bits. So if I have 4 bytes, that's going to be 32 bits. So if I have 8 characters in a hexadecimal value, that would actually be a 32-bit value. So this actually fills all 32 bits in num1. Likewise, if I have 4 bytes, if I have 2 bytes and a short, that's 16 bits. So since each of these is 4 bits, if I have 4 hexadecimal characters, this fills up the 16 bits with some particular bit pattern in num2. Okay. And so on. And we didn't end up filling up the whole array here. We only filled up the first character in our bytes character. Okay, the first thing we do is we queried the size of S here. So notice it comes out as 24 bytes. Okay? So that's something you might want to keep in mind. This might become relevant to some of our assignments and things. Most computer architectures will have bad performance if things aren't aligned on the size of access. Okay, so since we're using a 64-bit architecture here, we will get better performance if we align things on 64 bits or 8-byte boundaries. So at 8, 16, 24, 32, so on. Right. So even though the structure only takes 23 bytes, the C compiler, in order to improve performance, will actually allocate 24 bytes whenever this code is compiled here, whenever we create an instance or like an array of bytes. Right. So that's why I ended up with a size of 24 here. So, real quick, we can test that. So, for example, if I increase this, let's say we made this 10. So now the number of bytes would have been 25 instead of 23, since I increased it by 2. So if I recompile this and run it, we'll see now that it aligned it up to the next higher size. So it aligned it up to 32. So basically, the bytes from, if I have 25, the 26 through the 32nd byte are just not used, right? But that, so even though we have some unused space, the performance hit by accessing these in non-64-bit or non-8-byte boundaries would outweigh the wasted space that we have. So anyway, let me go back to what we had, just so my comments make sense here. So if we rerun again, we should be a size of 24 for our structure here. Okay? Even though we've actually only got 23 bytes in total in our struct. So the first few commands here are just showing the basics. So we're assigning all these. Some things that may be tricky. So this is really, the PTR actually holds a memory address, right? So by doing this, we're actually we have the address of this character array, which is probably in a constant section here. That's different from bytes. So this, again, bytes is going to refer to the base address of the array here, and then we can index that 0, 1, 2, 3. But yeah, those 8 bytes are actually going to be held in memory wherever we allocate our S structure here, right? And maybe this wasn't a good choice, but we use byte and bytes, so don't get those confused. So one of these is an array of 8 bytes. One of these is a single byte. So that will actually hold the bit pattern, the ASCII bit pattern for the single byte here, whereas bytes holds the base address for these 8 characters. That's allocated though as part of the structure here. So if we display it, we're just showing the member access operator, right? So, when you use %s for printf, this expects the address of a character array that's null terminated in C. So this will display the hello, what we pointed the pointer to, and we just display the number. So in in decimal, that is, this is the hexadecimal version of this 32-bit integer, and that's the decimal version of if we convert between hexadecimal and decimal, and that single byte held C. So we can have pointers to structures. So here we say SP is just a pointer to the S structure, right? We assign it the address there. So here is our example of using the dereference and member access operator. So this should get exactly the same result. So since this is pointing to the same contents, S here, if I dereference and access these member variables, I get exactly the same output. So we get the same hello, the same integer, and the same character. So beginning from here, this will be similar stuff to what you'll need to do in an assignment for the class here. So here we're showing that we're going to recast S. We're going to get the address of it, but we're going to treat it as just a pointer to some buffer of characters. Or basically, this is the basic way that we can treat something that's just a stream of bytes or a block of bytes in memory here. So notice we're using pointer arithmetic here. So since it's a stream of bytes, this will just add 12 to where the address is and 13 to the addresses and display those as characters, right? So since we're using %C, and since this is supposedly a pointer to characters, this pointer arithmetic, after we dereference this, will display the character values here. So first of all, let's look at an offset of 12 and 13 in S here. So, to understand that, that's why I put the byte counts here. So, the bytes 0 through 7 are going to be in this address here, right? And if I go to a byte offset of 8, so 8, 9, 10, 11 will be the one for this 4-bit integer. So 12 and 13 will be the 2 bytes here for the short. Okay? And we assign 41, 42 to position 12 and position 13 in here. And just as a reminder, I don't remember if we've shown an ASCII table before in this class, but you can just Google like ASCII table. So indeed, as was in the comments on that code, A is going to be encoded, if we're using ASCII encoding, as 41 hexadecimal, and B is going to be encoded as 42 hexadecimal. So if you look at that, just to clarify something here, if you look at that, you might expect that the access we were just doing, the offset, the 12th byte offset, would give you 41, the ASCII A, if you interpret that byte as a character, and it would give the offset 13 from the start of the structure as 42, or the ASCII B, right? But in fact, so again, remember the first thing we did here was we output the offset 12 and 13, and you see that it's kind of reversed. That's basically, as noted in the comment here, is that RISC V is little Indian. So the 2-byte short is going to be, so when we assign a hex value 4142, the least significant byte gets, the little in gets installed at the lowest address. So the lowest address is offset 12. So 42 actually gets assigned offset 12, the least significant, and 41 gets assigned to the most significant. The most significant bytes get assigned to the higher address. That's just what little Indian means, little Indian encoding. And basically, I mean, little Indian, a lot of hardware architects don't like little Indian. They think big Indian is more natural. But x86 and ARM use that, and it looks like RISC V is going to end up using little Indian as well. It's kind of won out just because of momentum. So anyway, I mean, that is what's happening here. So we end up with the B, the 42 ends up at offset 12, and the A 41 ends up at offset 13. But if you look down a little bit further here, if we treat this as a short, it's a little bit tricky, but you might need to do this in your assignment. So we're still using the CP, the character pointer, so just as an array of bytes, and we do our arithmetic offset of 12 bytes from the start of whatever's in the address of the CP here. But then we cast this as if it's pointing to a short instead of a byte, instead of a byte array. So if you do that, and then you output the hexadecimal value, it looks like 4142 again, like we assigned it to that short integer up when we created and when we assigned the num2 member in the structure that we had here. So the same example, but using the, I guess that was num2, so using num1. Num1 has an offset of 8 from the start of our structure here. And we're doing the same thing. We're accessing it byte by byte. We're still just using the cast of the CP here. So adding 8, 9, 10, 11 to access the byte offset 8, 9, 10, 11 in the structure here. So as a reminder, let's go back and look at what we did here. So num1 was offset at positions 8, 9, 10, 11 from the start of the structure here. And we allocated, we initialized num1 to have the hex value 11223344. Okay. So again, because of the little Indian encoding in our RISC-V architecture, the lowest address, so the offset 8 actually ends up holding the 44 byte, and then offset 9 has 33, offset 10 has 22, and offset 11 has 11 in it. So that's what we see in the result here. So the offset 8 has the least significant byte that we assigned in there for 4, then we 3, 3, 2, 2, and 1. All right. Then, but if we do the same trick, so if we cast that so that we convince it that we're pointing to something that should be interpreted as a 4-byte integer, which is how we do this. So we take CP, add 8 to that, and then cast that into a pointer to an integer, so a regular pointer to a 4-byte thing. And if we send that to printf, like using %x or %d, which will interpret this as a 4-byte integer value or a 4-byte hexadecimal value, we get it in the order that we assign that we expect. Hexadecimal 11223344 here. Okay. So before I leave this example, I'll just say that to me this is probably the easiest way to do the conversions that you need for the assignment where you have to do this stuff here. So you can do kind of one where you assign the pointer to the beginning of the array of your structure that you have here. So CP is just going to be the address of the start of the structure here that we can treat as a byte array and get any particular byte position in the byte array or the character array, pointer to that array, that block of bytes in memory. And then there are different ways you can do this, but I find it easiest to go back is if you go that and do a cast. So this is going to be take that address, add 12 to it, and then we can easily make our printf treat this as like a short that we dereference the short. So I should have pointed out that we are dereferencing this. This is really just an address, and then when we dereference, it'll get interpreted as 2-byte short, even though we display it as a hexadecimal or as a 4-byte short when we dereference, and treat this as an integer pointer here. So we get a 4-byte or a 32-bit short on the dereference output here. All right, so that's it for the topics I wanted to cover about structures and pointers to structures and kind of manipulating them down at the byte level. So just to summarize the things that we discussed in this video. So a structure is a collection of one or more variables of different types. They're grouped together under a single name. So this is really a basic computer science concept. So, if people talk about records or row of a database or user-defined data type, we're really getting at kind of the same idea here. So you use the dot for member access of a member of a structure, of a field of a structure. As we showed, a couple of things that are good to keep in mind for this class, for the RISC-V architecture, a structure will be byte aligned for 64 bits or 8 bytes. This is for performance reasons. So, if you have some number of bytes that's not a multiple of 8, it will actually pad your structures up to, 8, 16, 24, 32, that number of bytes. Right? This will help performance in a normal, if you're running it on actual real hardware. And also, I probably should have added this in my summary here, but the RISC-V architecture is a little Indian, like x86 is, and ARM. So that may or may not surprise you. I mean, it feels backwards to most people when they first run across this, but the least significant byte actually ends up in the lowest address, and the most significant byte in the highest address in memory. That's just how things are laid out for little Indian here. We didn't really show examples, but you can create arrays of structures. You can pass in structures to functions. You can actually return structures as a result from a function in ANSI C. We won't. Usually when we're passing in a structure, we will pass in a reference to a structure for the system call to fill it out, like we showed in this video here, so that we get it returned back as the reference instead of returning it back as the result from the function. And just like you can have a pointer to a basic data type or a pointer to an array, a block of a data type, you can have a pointer to a structure or a pointer to an array of structures even, which we didn't really show in this video. There is a special operator, which we will use a lot in this class, that performs both the member access and the dereference. So it follows the address to dereference it, and then it accesses the particular member in there using this special arrow operator. All right. So that's it for this video. As usual, I hope you are finding these useful. Let me know if you have feedback or things. And I will have pointers. I'll have references to the video description for the things that we use in these videos or in our class resources. Yeah, that's it. So I hope to see you in class.